Welcome back. Today we are taking a closer look into the fascinating world of high-performance data engineering. Imagine processing 1.2 billion records per hour. Sounds ambitious, right? Well, with the use of Apache Kafka and Spark, we are making it a reality. And we are not stopping there. We are adding ELK Stack for logging, Prometheus and Grafana for real-time monitoring, and Kafka Schema Registry and Control Center for visualization. So buckle up, you are in for a treat. We'll start by mapping out the architecture of the system, showing you exactly how each piece fits together to achieve this incredible throughput. We'll start with Kafka Producers, then head on to Spark's distributed processing unit with the master worker architecture. Every component in this video plays an important role in the grand scheme of things. The next thing we do is tackle the numbers, where we discuss the storage estimation. When you're expecting billions of records into your system, you need to plan ahead by calculating to the nearest T what your storage requirements will be and cater for growth demands, especially in 3 or 5 years' time. Once the theory is clear, it is time to get hands-on. We'll build this entire architecture from scratch using Docker Compose and discuss some interesting concepts about these architectures. If you have ever wondered how Python and Java will compare in real world, then this video is going to be interesting for you. We put them head to head in this video as Kafka Producers, and spoiler alert, Java blows Python out of the water with 250,000 records per second. But wait till you see how we push Python to its limit. Then we moved into the art of the pipeline with Apache Spark. We explore the structured streaming capabilities and how to fine-tune the properties for optimal performance. The final thing we do is real-time monitoring. This is very key for any production-grade pipeline. Prometheus and Grafana will help us visualize the performance, while ELK Stack is going to ensure we never miss a critical log. By the end of this video, you not only understand the how, but also the why behind every decision in this architecture. Are you ready to level up your data engineering skills? Grab a cup of coffee and let's get started. So why don't we get started and see what the architecture is going to look like from the ground up? We're going to start by piecing each of them together and see what the relationship is going to be, what kind of data is expected, and what the data output will look like. And some of the decisions that we'll be making will shape the rest of the videos that we're going to be doing subsequently. So right now we have Kafka, of course. So Kafka is going to be somewhere here. Our Kafka is going to be here. So the decision of Kafka, the type of the Kafka to use, will now be dependent on you. Now you can decide to use the Zookeeper type, which is the more like the old version. I'll call it version 1. Not really version 1, you get the point. But I'll say the old version of Kafka. Now the reason why you might want to use that bit is if you have other systems that are going to be connecting to Kafka or Spark or whatever architecture you have, and they are really dependent on Zookeeper, there's really no point. If you're using something like Druid is by default using Zookeeper, right? Until maybe they have a way to detach the Zookeeper from there. So if you're using something like Druid, right, which has Zookeeper in it, it's an additional overhead. So if you want to connect your Kafka to that as well, the same Zookeeper, you're good to go. So you can leverage the Zookeeper architecture with that bit. But if your system does not necessarily connect to something like Druid, which is reliant on Zookeeper, there's no point using Zookeeper. You could have other additional justification for using or not using it, but yeah, you get the point. Now we have Kafka. So in our case, we'll be using the kraft mode. So I'll call this kraft mode, right? So we're not using the Zookeeper mode in here. But in case you decide to use Zookeeper, I'll just keep it here as Zookeeper. And I'll start this. So this is not what we want to explore for now, but yeah, you get the point. So now we have a streaming agent, which is going to be here. Streaming. What's that? Is that streaming? So we have a streaming, right? So we are streaming into Spark, right? So Spark is going to, if I can only write Spark, right? We have Spark, which is going to be the master worker architecture. So we have the master here, and we have the workers. So we have 3 workers in our case. And the reason why I'm using 3 workers is because of the kind of system that I'm using. in your system, if your system is not as high-end as mine, or is maybe more powerful than mine, you might want to increase the number of workers, or scale it down depending on what resources you have or the compute power you have, right? A simple worker, one worker is fine. One master is okay. You don't necessarily need to have multiple workers, right? If you don't have enough resources. But in my case, I have the resources to power 3 workers, so I'm good to go, right? So I have my Spark with the master worker architecture. These are the core, right? What that means is we need to find a way to produce data into Kafka, right? So if you have our producer is going to be somewhere here. So we have the producer is going to be somewhere like a web app, right? It could be a web app, it could be an API, it could be an app itself, maybe a Python or Java app, or whatever app you decide to use. That's going to be our producer. So this is going to be the producers, right? It could be one of them, it could be multiple combination of them. Yeah, that's left to you, right? But if you're using web app or API, then you need to have something like a load balancer. That means the data is coming from some front end. So you have a load balancer, right? So in our load balancer, the job is just to like evenly distribute the data that is coming into the system. So it's no system is having to get choked with work, right? So we have the load balancer sending data into the picture with the web app, API, the apps, and then we have the Kafka in KRaft mode with Zookeeper if you prefer. Then we have the streaming agent, which is the Spark in our case with the master worker architectures. But we still need to make sure that the data that is coming in from this app, API, or web app is conforming to some standard. There is no easier way to do that than to use something called Schema Registry, right? Schema Registry. I'll just leave it at that. You get the point. Yeah, Schema Registry. So Schema Registry allows us to do that easily without issues, right? So for that to work, it's a two-way communication. It's not only one way. Then we can decide to visualize whatever you have on the back end if you're comfortable with the code, with writing the script yourself. If you're not too comfortable with that, or you need to expose it to some users that are not so technical, then you need some visualization UI. So now the decision to use whatever UI in this case is left to you. You can use the Confluent Kafka, the Confluent Cloud Enterprise UI. You could use the Kafka UI. You could use even the one that gets shipped with something like the IntelliJ ecosystem with the big data tools. You can use that to visualize that the data in your Kafka. So yeah, the decision is left to you on that bit. So I wouldn't talk too much on that. Now, once the data comes in from the load balancer, producer, then it goes into Kafka. We visualize it on the UI. The Schema Registry is making sure everything is backward compatible or forward compatible or full compatible in terms of compatibility options. We're not using Zookeeper, and we're streaming straight into Spark with the master worker architecture. What that means is we need to have an output here, the layer that the data is going to be streaming into from here. Yeah. So we're streaming straight into a BI or analytics tool, right? BI or analytics tool. However you want it. Could be like a RDBMS, it could be like Elasticsearch, it could be like a UI, it could even be Streamlined or whatever you prefer. But in our case, if you prefer to use something like the ELK Stack, which is going to be really useful in our case, we have the Elasticsearch, Logstash, and Kibana, which is we are streaming in there too, right? Yeah, you can ignore my writing, right? So we have Elasticsearch, Logstash, and Kibana. So the data in there, you can write directly to Elasticsearch in there, and you're good to go. And you can ship the logs across board. But what you also need in this case, and visualize on the dashboard on Kibana, everything seems fine, and we can actually leave it as it is. But in a production environment, that will not be the case. You still need to find a way to monitor what's going on here, so you know which system needs to be improved or which system needs additional resources. To do that, Prometheus helps us with that. So we are going to start, shouldn't be starting from, I think we should start from, should start from somewhere here to the end. Yeah, so we have the monitoring bit, which is Prometheus. I found that Prometheus is very useful when it comes to monitoring, and to visualize what you have on Prometheus, you need to use something like Grafana, right? So whatever you're shipping from Kafka, UI, Schema, Registry, Zookeeper optionally, Spark Master Worker Architecture, your ELK Stack, or whatever BI analytics tool you want to keep an eye on, Prometheus helps you to collect those logs and ship it to Grafana, and you can have your dashboard to monitor the traffic and see if the throughput you have on the architecture is enough to cater for your data that is coming into the system, or you need to scale up at any point in time. So this is going to be streaming, right? Streaming, STREAMING, right? So yeah, that's it. And once you monitor that, the only bit that is left is the storage. Where will all this data store go into? Because if you're like myself, you don't have 100% resources, or you're not using the cloud environment that you can easily scale up, then you have to monitor what's going on in the storage, right? So we need to have a storage where all this will be, and the storage could be like RDBMS if you prefer, or it could be RDBMS, or it could be like an HDFS where you store the data into, or even you could use something like S3 or any other storage options that you have. But yeah, I think at this point, so that would be like a major overview of what we have on our architecture. Now, how do we do the calculation of what the storage is going to look like? All right, how do we know our storage is enough or will be enough, or to prepare for like some product? So we want to prepare for like the future, right? I don't know why the future just keep escaping me. So we want to prepare for the future, maybe in 2 years time, or even 5 years time. How you can easily prepare for something like that. So we have the storage section. So let's go through the storage and see what that will look like. We have the storage. Now let's take a sample data that we have here. I'm going to just pull up one sample data that I have here. So for the storage, we need to have the granularity level of what the data is going to look like. So we are going to have a fact transaction here, which is the transactions that we produced and we keep track of. I'm going to make this a little bit make more sense by the time we get to that bit yet, but to get the storage out of the way and we can make this make a little bit more sense and cleaner, we're going to have a JSON object here. So let's say we have a JSON object which is having transaction ID. Yeah, our transaction ID is going to be somewhere there. It's going to be a string or UUID. It could be an integer if you prefer, but yeah, that's left to you. Then we have amount, right? The amount you have in here, yeah, amount is going to be a decimal or a floating object, so that's left to you. So I'll call this let's call it float to keep things simple. And you have a user ID who performed the transaction. This is going to be a string, right? Of course, UUID is going to be a string, right? Or it's a 36 character string. You get it? Yeah. We have the transaction time, which is going to be a date, right? But in our case, we're going to be storing that as a milliseconds, right? So in milliseconds, it's going to be like a big integer, right? And we're going to estimate what the size of all of this is going to look like by the time we get there. Then we have the merchant ID, which is who the merchant is. It could be like merchant 1, merchant 2, merchant 99 or something like that. So this is going to be a string, and a sample record is going to be like a merchant _1, and the transaction time is going to be like 1 2 3 blah blah blah, and user ID in this case would be like we could have user underscore 1 2 3 4 5 6, right? The amount is going to be something like 1 2 3 4 5 6.78, right? And UUID is going to be something like 102 something like dash U3 whatever blah 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 up to 36 characters, right? I know the writing is not so great, especially with the pen, so yeah, just please manage that. We have the transaction type is going to be something like a purchase. Yeah, I'll just start with the data type. Yeah, it's going to be something like this, a string, and the sample record is going to be like a purchase or refund. Now we have the location. Location it's going to be like a location ID. So we have the location one. Of course, it's going to be a string. So I'll just clean this up. And it's going to be like a location 1, location 9, or something like that. We're almost there. So we have the location, we have the payment method, right? So it's going to be a string as well, and that's going to be like a credit card, PayPal, bank transfer, and stuff like that. Yeah, we leave it at that. And then we have the, if it is an international transaction, is international. Yeah, if it is international, so that's going to be like a boolean, so it's going to be true or false, right? So it's going to be a boolean, could be true or false, right? And the final thing is going to be the currency, right? Currency is going to be a string of 3 characters, so it's going to be something like GBP. Yeah, so with this we can easily estimate what the data is going to look like, or what the storage that we're expecting, especially for this fact table, that will look like. So let's start with the transaction ID. So if you have a 36 character here, we're going to be expecting something like 36 bytes, right? And we're estimating everything in bytes, so we're not using bits or something like that, because everything needs to be at the granular level possible, right? So the amount is going to be 2468, right? So let's cater for 8 bytes, right? 8 bytes. Then for the user ID, we have user underscore 1 2 3 4 5 6. So we have 2 4 6 8 10 11. So let's cater for 12 bytes. It could be more. This is just like an estimate. It could be more. So we're going to leave some space for that. We have the transaction time, which is a big integer, so 8 bytes. Because it's compressible, integers are usually heavy they utilize heavy compression, so it's really good with that. We have the merchant ID, so the merchant ID is going to be merchant 1, so we have 2 4 6 8 10, right? So let's cater for 12 bytes here, because we could have merchant 99 or something like that. Yeah, that makes sense. And if you have more, we're going to have extra space for that. Transaction type is purchase, refund, and stuff like that. 2 4 6 8, right? So let's cater for 8 bytes here. The location is location 1 2 4 6 8 10, right? Let's cater for 12 bytes here. Payment method is going to be credit card, bank transfer, and stuff like that. So let's cater for 12 bytes here as well, maybe 15, because it looks like bank transfer is about 15 records, right? This is 4, so let's cater for 5 bytes. And the currency is GBP, so let's say 5 bytes as well. Yeah, so if you add all of this together, 36 point plus 8 plus this is 10, 10, 10, 15. Yeah, so we have about 120 bytes here. 120 bytes. So which is good. So we know for our raw table, in this case, the data that is going into this particular table, it could be a fact transaction or whatever table name we give to this, is going to be roughly for a single record 120 bytes. So what that means is if you're looking at let's say raw is 120 bytes and we have a total which is expected in 1 hour, right? 1.2 billion. So we are expecting our total number to be 1.2 billion in terms of size, right? So if you multiply these two together, you're going to get something around maybe 216 billion, right? 216 billion. Yeah, something around that. Yeah. Maybe I'm wrong, but yeah, let's just estimate this as 216 billion. And what this means is 216 gig, right? If you convert that into gig. Okay, so we have 216 gig per hour. Okay, and that's a heavy one. 216 gig in this case. So what does the Kafka overhead look like? Because we still need to understand what the Kafka implication of this will look like. So we are producing 216 gig record into Kafka. The good thing is if you are producing JSON objects, you can compress on Kafka. So with the compression, let's factor in compression. We have different rates of compression. So let's say we have 5 times rate of compression. So 5 times compression. Yeah. How many replicas do we want to have on Kafka? So if you have 1 replica, and if you have 3 replica, yeah, for 1 replica, we're going to have at 5 times compression. That will be 216 billion. 216 billion divided by 5 multiplied by 1, right? So that will give us maybe 40, 45, 20, yeah, about not 20. Yeah, that will give us about 43 or 44 gig, right? 43.6 or something like that. 43 gig. That would be like for 1 replica. But if you have 3 replica, you have to multiply this by 3, right? So that would be like about 130, 129, 130 gig, right? For 3 replica, 5 times compression. But if you don't have, maybe you're using Snappy here for the compression or gzip, anyone you're using. So let's say you are able to achieve 5 times compression. This is what your 3 times replica will look like, and this is what your one replica will look like. But if you don't have any compression, so let's say you have a 1 times compression, you don't have 0 compression, there's really no point of writing this. You already know it's 216 gig that you're going to have. So what that means is if you are scoping for a year or like a day, so in a day we have 1 hour for 26 gig. So let's calculate that. So we have 1 hour equals to, let's say we are using 3 replica for and 5 times compression on Kafka. So we have 130 gig, right? So 24 hours will be equals to x. So we multiply these two together, and our x is going to be 24 times 130 gig, right? And that will give us whatever we calculate. I'm going to do the calculation. So if you have, let's do that. So 130 gig multiplied by 24, that's 3120. So we have 3120 gig, and that's 3 terabytes, right? So which is 3 TB per day. And if you have 3 terabytes per day, if you multiply this by, let's say 30 days, yeah, this is a day, so let's go multiply this by a year, 365. So we have 3 terabytes multiplied by 365, and that will give us 1138800 terabytes. Yeah, I'll just clean this up and make this a little bit cleaner. So we have 3 terabytes in a year. We have 1138,800 terabytes. So that's what we're expecting for 1 year. So to scope for like 3 years now, so we need to have like a growth rate. So we are using we're sticking to the 3 replica with the 5 times compression for a year, which is giving us 1.13800 terabytes. So that would be we just need to scope for 20% increase. So usually it's like about the size is going to be more like the base multiplied by, that's a multiplication sign, multiplied by 1 plus the growth size raised to power n. So yeah, so that means if our 1 year is 1.138, so in 2 years we're going to have our size n is going to be the base of 1,138,800 multiplied by 1 plus, let's say we are having 15% to 20% growth. So let's say 20% growth rate raised to power 2, right? So size of 2 years is going to be 1138. So we have 0.2 there, and that's going to be 1138,800 multiplied by 1 plus 0.2 raised to power 2. So we have 1 sorry, not 1 is 1, we have 1,639,872 terabytes. Yeah, I think that's petabytes, right? So if you divide it by 1,000, so we have, which is approximately 1.639 petabytes, right? And yeah, that's what it's going to look like. So of course, if it's another 20%, you just need to change the formula by 2 or by 3 by 5 years, and you can have, so but maybe by 5 years you could have for year 5, size of 5 records in year 5 is going to be 1,138,800 multiplied by 1 plus 20 over 100 multiplied by 5, right? And raised to power 5, and that should give you approximately maybe 2.3, maybe 600 or something like that petabytes. Yeah, that would be something roughly around that number for 5 years, right? So let's say we have something like this. So we know for sure we're going to be needing a heavy data size to host 1.2 billion records per hour. Now that's the first bit of this entire thing that we need to take care of. Now the second bit is now to be able to keep up with the production of 1.2 billion records per hour, which is going to be an heavy task or equivalent task if you're using something like Python, to be honest. If you're using maybe Java, you can still like push your local system up to that point. But yeah, let's see what that look like once we get in there. So let's clean this up and make this a little bit more better. Now that we are making this better, we have our load balancer, which is the initial guy that we had as if you are starting with a web server API or data producer or whatever it is. In that case, if you're using web server or API, you're going to start with a load balancer, which is going to be sending data into the web server. And in that case, there's an arrow missing downward in there. I'm going to add it much later. So we have our load balancer here, so which sends data into this guy. Just like we said before, that sends data into Kafka, then Kafka into Spark, and then we have a storage, which is our data lake or our DBMS or whatever you want to store your data into in there. Then on the right hand side, we have your monitoring, which is Prometheus and Grafana, and then log in with ELK Stack. Then you have your BI analytics tool, which is on the UI here, right? So in that case, it could be Power BI, it could be Tableau, it could be Streamlined, it could be Elasticsearch, whatever you want to use, right? So of course, you still need to like visualize the login on Kibana or something like that, right? So let's take a look at what the system level architecture looks like. Just like we had in the high level architecture, we have in our case, we're going to have a Java producer, a Python producer, which produces data into Kafka. So a Kafka is stored up as a KRaft mode, which is having a controller and a broadcast, right? So in our case, we're going to have 3 controllers because that makes up a quorum. You could have if you have one controller, then you wouldn't have a quorum in that case because that particular controller will be the leader, right? So for you to have a quorum, you need to have, you can't have 2 because that will be like a tie when you are making an election, right? So you need to have a minimum of 3 as the recommended approach to selecting a quorum. So you have 3 controllers in a quorum. So one of them will be the leader, and the rest will be like the follower. So if the leader goes down, the data is replicated onto the other controllers, and the metadata and other things get picked up by the rest of the controllers. While the brokers, so you could have one broker, you could have as many brokers as possible, but in our case, we're going to have 3 brokers, 3 controllers that are controlling 3 brokers, right? And specifically, I have my schema registry tied to the brokers because technically the brokers will be interfacing with the schema registry. So not necessarily the controllers, the brokers themselves. Now we visualize everything on the control center to see what's going on with the data that is being produced on Kafka, how many replicas we have, do we have any partitions that the data are going to, whatever partitions that you decide to use. Now in our case, we have Apache Spark, just like we discussed. Apache Spark with the master worker architecture. The first one which receives the data is the master and distributes the data into the workers. So they get it done and then ships it back to the master. Then we can ship that into Elasticsearch, and Logstash, of course, visualizes everything. Kibana for the visualization of the logs, and Elasticsearch. The most important bit is the monitoring here. Not really the most important, to be honest. We could do away with it, so it's like optional. So we have the monitoring with the Prometheus and Grafana. So whatever is being shipped across your controller, the broker, the Spark, master worker architecture, ELK Stack, you can collect those logs with Prometheus and ships them to Grafana. We're going to see what that look like in here. Of course, the storage is going to be on my local system, so I'm not going to be using HDFS or S3 or data lake or whatever it is in that case. I'll just be using my local system to just run this. Obviously, that's not a production ready system because it's my local system. So to make it production ready, you need to have an HDFS or a data lake or S3 or whatever it is that's going to be the underlying storage architecture for your system. So yeah, so that's what the entire overview of the architecture look like, and you know what we're expecting per hour. We're expecting roughly about 216 gig uncompressed data, but if you compress it, we're about, maybe with the replicas on Kafka, we're about 130 gig per hour. So yeah, let's see if we can push that. Obviously Python may not be able to push 300,000 records per second, so yeah, we can employ the service of Java to see if we can push up the data up to like 100k, 150k, maybe even 200k per second. Yeah, let's see what that look like and get into that. So thank you very much. If you watched the video up to this point and you've not subscribed, and this is your first time in the channel and you've not subscribed, please don't forget to click on the subscribe button, like, comment, share this video to your colleagues and friends. These are the things that motivate me to continue producing valuable content for you. So thank you very much for the support, and I'll see you in the coding section. One thing that I forgot to mention in the architecture section is the importance of other systems as well. So don't forget, we're only scoping for the JSON objects that we'll be using for this project. Of course, you still have other tables that has some records and some dimension tables that had additional records in the DB that you'll be working with. So you need to, of course, scope for those as well. We're only scoping based on our scope for this video. We're scoping only for the data that we're producing into Kafka and we're consuming, not really or necessarily the entire DB. So if you have other DB, let's say like an e-commerce store, maybe you'll probably be needing double that, because only that production alone that you're seeing has some dimension data that are connected to it as well. And then you have some other data in the tables on your DB as well, so that will be hosting some other data. Okay, so in our case, yeah, with that said, let's get into creation of the project and get started with that. Okay, so what I have right now is the Python PyCharm environment. So I just created a new project and I'm using PyCharm. So if you are using PyCharm as well, I would recommend you use it. If you don't like it or you want to use a different ID, that's all well and good as well. So let's say Kafka Spark, Kafka Spark 1.2, maybe Kafka Spark arc is fine. Kafka, I don't know, I'm bad at naming something, maybe it's just me, I don't know, but I'll just leave it at that. So I'm using Python 3.9, but I could change it to something like 3.10 or 11 or something now. I don't know, as I have preference for 3.9. So if you prefer to use the latest versions, be careful, because some of the packages may not be compatible with the latest version of Python. I think 3.13 as at the time of recording this video. So I'm using 3.9. If you can push it to 3.10, but maybe from there you have to be watchful of the packages that you use going forward. So I'll create a project with that and create a new project. Okay, so yeah, so that's created. So the first thing we want to do is check the environmental setup. So if I touch my main.py and inside my main, I need to first increase the size of the screen so it's visible to everybody, and it's easily you can relate with that. I believe this should be, let me check, is this visible to, yeah, that should be visible enough. Yeah, that's good. Now with this taken care of, so the first bit is to now go into the architecture of the system. So based on what we have, let's keep these guys for now. Let's start with the Kafka Kraft mode architecture. So for that to work, we need to touch our Docker Compose .yaml. So the Docker Compose.yaml file is what we'll be using to containerize everything that we'll be working with. So I have in my notes here, it's a lot of coding. So what I'm going to do is for people that, for the public, I'll just maybe copy paste the architecture, but for some specific people like for people that subscribe to membership options, they have the chance where we can discuss this in more details. But for now, I'll just copy those architectures in place and we can discuss them much later. So we have our Kafka controller, so which looks like this. I'm just going to get our services in. So we have our Kafka controller, which has the first Kafka controller with the Kafka node ID 1, and the rest is as it is. So we are going to have the second controller, and here's the second controller. So similar to this, but it's a little bit different because we have our ID is a little bit changing, and of course the controller is the same. Of course the container name and the host name and all that is also changing as well. Okay, and then the last bit is the last controller. Just copy that as well into my controller, and my controllers will be like this. So we have 3 controllers, all with the same and you can see my quorum. I have 1 controller here, 2 controller, and the 3rd controller all connected together in the quorum vote. So it's easy to have our controllers during quorum voting to choose the leader within these three. So, but if one goes down, so either of the two will take the place of the leader and pick up from where it stopped. And I'll just get in our brokers, broker 1, 2, and 3, and yeah, I'll just comment out some bits and pieces until we get there. So for now, I just commented I'll just remove this bit, and we're depending on the three controllers, right? I'm just removing the JMX exporter for Prometheus. For now, we're going to add it back, but for now, let's remove it from there. I'll just uncomment this, and the JMX exporter as well. We go away from there, and the last bit for here, uncomment. Yeah. So like I said, you don't necessarily need all of this, to be honest. So you can use just one controller and one broker, and you're good to go. But if you want to simulate what a production environment will look like and be able to capture 1.2 billion records per hour, then you probably need to have a similar architecture that we just discussed. Okay, so our brokers are ready. So let's throw in our schema registry. The schema registry is going to be coming in from Confluent Inc. So we'll be using the CPU schema registry 7.51, and yeah, for now we can ignore the JMX exporting for Prometheus. Yeah, we can always get back to that much later, but for now let's skip those, and let's get in our console. So the console, I'll be using the Red Panda console. Okay, so if you prefer to use a different console or UI, just change the parameters and make sure everything is working fine. And I need to depend on the schema registry to make sure everything is working fine. Good. And yeah, so I'll leave it at that. So we have here we have this bit taken care of. All of these bits are taken care of. Now, for people that are like the members, you need to understand something here. I need to minimize this bit so it's easy to understand what's going on. So our controller, once you create a controller, you have the image, the container name. The container name, of course, you don't have to necessarily do this, but because you are referring to this particular container with the broker as well, so you need to make sure that the container name is static. Otherwise, it's going to append it to something like Kafka Spark Arch -iPhone Kafka controller 1 or something like that. But if you give it a container name, then it's not going to do that. It's just going to give it retain this particular name. And that's why during the quorum voting, we have Kafka controller 1, Kafka controller 2, and Kafka controller 3. So of course the controller is the listener name, the plain text. So if you're using a security based Kafka and you want to secure your Kafka with some credentials or SSL or something like that, then you have to change the plain text to the protocol you're using. Usually it's SASL, so it may not be plain text, so because it could be susceptible to sniffing, network sniffing. But you get the point. So yeah, so that's like another level of security and all that. Yeah, so but we have a volume. The volume here, we are mapping controller data 1 into our Kafka data, which is going to be inside the container. Of course, it's going to be on the network. So the node ID is this and the controller is that. That's fine. And for the same thing happens for the two other controllers. The only difference is the node ID would change and the container name would change as well. Then we do the mapping of the controller data. The same thing happened for the third one. Now this is where it gets interesting. For the broker, you make sure that of course the name stays the same. And if you look at this page, now look at this is where it gets a little bit tricky. We're exposing the port of 29092 on my internal system, but inside the port, inside the container is 9092, and that's the plain text ID. When I'm listening for connections from other containers, right, which is the internal containers that are on the same subnetwork, right? In my case, on the same subnet, here I'm having my plain text as 19092, and the plain text host, which is the host that is the port that is hosting that, is 9092 on the same IP, internal IP, right? So the 9092, you can communicate with that internally, but for other containers, you have to connect to 19092. Now for the advertised listener, so this is like the Kafka listener, that more like the internal Kafka listener, but it's still not advertised. So you need to advertise it for other people to be able to use that. More like you have a private or internal IP and port. You have external, just like the port mapping, right? You have the external where you advertise the port. So in our case, we are advertising Kafka broker 19092. So for the broker. So anybody that wants to connect to this broker needs to use this Kafka broker 1 on the same port, 19092. But if you want to connect from my local system, I need to connect from 29092. Please don't get confused with that. Okay, which is like if you're using plain text those on my local system, you can use localhost 29092. But if you are inside the network, you can use Kafka broker 1 as the name and the port here. The rest is the same. I'll just uncomment this bit to make sure that my Kafka controller quorum voter is the same, and we are depending on the controllers to be ready. And for the broker data, we need to map the volume. We don't have the volume mapped right now. We get to that shortly. And then the broker here as well, just like we did before as with the other guy, the internal mapping on my local system is 39092. Internally is 9092. But I'm exposing 19092 as the listener. So when you are connecting to this with the advertised listener, which is the like public advertised listener, you are connecting to this Kafka broker 19092. The same thing with the quorum voter as well. We have to depend on the controller. Of course, we need to map this. The same thing happens to the last guy here, and we should be good to go. So we don't have to like repeat the same thing over and over again. Now, this is where it gets a little bit different when it comes to the schema registry. Now, you could map one of them, but if that goes down, then the schema registry will be affected. Now, what you should do is the three brokers that has the same port and IP address that has in our case the same port but different IP address, which is Kafka broker 1, 2, and 3. You want to supply everything to the schema registry. So if any of them goes down, the schema registry can pick up from the other party that picks up from there. And the topic that is going to be created for the schemas on Kafka is called _schema. I'll show you how to see this on the Red Panda console. We get there shortly. And the listener URL is this. So any IP address but the same port that is referring to the schema registry, that's the one you use. Now the final thing is the console, which is here. So we're using the Red Panda data console, the version 2.5.2. You can use the latest version, but you have to change the configuration a little bit. So I'm mapping on 8080. I need to add quotes to that. That's why you see the script will be underneath it. Then I'm sending the brokers. If you look at this bit, I'm sending these three brokers as the Kafka brokers. Now the console alone does not function without the brokers. So the brokers you're seeing here, the three brokers that I'm using in the KRaft mode. And to enable the schema registry on the Red Panda console, you need to enable it and put in the URL for the schema registry. And it's no surprise, the schema registry and the port for schema registry has already been discussed. Then for the admin API, we don't need it. So if you want to relate with Red Panda over API, or you want to enable the administration API, you need to enable that. But for now, this has to change. It's not Kafka _broker, so it has to be maybe Kafka broker 968, yeah, 9644. Yeah, you need to change this, but I'm not using it, so it's disabled. I'm not using Kafka Connect. So if you want to like connect to maybe direct connection to Elasticsearch and ship data out of there, or you want to push those data to S3, you can use the connect to do that. You just need to specify those parameters, and maybe in a separate video we can go through how you can connect Red Panda console to all these environments. Yeah, and that's it. So the final thing is just to get the volumes in. Just get the volumes, and here are the volumes. So you have the controller data 123, the broker data 123. Now that's it. I'll just delete everything on my local system. I'm not using any of them, and I'll just do docker compose up in detached mode, and that should, I need a network, so my network is not there. That would be code with you, right? And that's it, really. Just start that up, and it's going to pull up all the images online into my local system. That should take maybe less than a minute to do all of that, depending on your internet speed. Okay, so it literally took 1 minute to set up the environment, and right now I have my containers created, the volumes are created, and yeah, we're good to go. So let's check this out on this dashboard. You can see my brokers and controllers are up, but the console is still not up. So let's check the schema registry. So the schema is started and it's listening for events. So I'll just start the console again and see if that picks up. And yeah, you see it started on 8080 and it's ready to accept connection. Good. So what I'm gonna do is move my, and on my Red Panda console, I have something like this. If you look into the topic, there's currently no topic, and if you check the internal topics, you have the consumer offset and the schemas that was created by the schema registry. You see these two guys, so I don't really need to change anything in there. So I don't need to show internal topics, so we're good to go. So if you want to check the schema registry, you can check here. So right now, the compatibility mode is set to backward. You can change it to transitive backward, forward, transitive forward, full, whatever it is you want. I'll just leave it as it is right now. And yeah, so we don't have any topic, so let's get in our topic and get started with the production. So our architecture is fine. For Kafka, if you look at this bit, we've taken care of this bit. So the only thing that is left is this bit and this bit and this bit, about 3 or 4 of them. So let's start with the master worker architecture. We already did this multiple times in the channel. So if this is your first time or you've not seen this before, you might have to take a look at those old videos. So I'm just going to copy the master worker architecture as simple as possible that we have it. So I'll just have my master and the worker. So I said I'm gonna have 3 workers, right? So I have my Spark master, which is inheriting from Spark common, and I'm exposing these ports on the master. And for the workers, I have this as my 3 workers. So worker 1, worker 2, and worker 3. Yeah, if you look at this bit, I'm using 2 cores and 2 gig memory for my Spark worker. So if you try 2 gig and your system is complaining of resources, you can try and downgrade it to 1 gig and 1 core. So that should fly a little bit. If it still doesn't fly, you might need to comment out the worker, one of these worker or 2 of them, to make it work. And the final thing is the Spark common that we are inheriting from. We could put it down or up, it doesn't matter. So what I'm doing is basically the image, the volumes, and the network, which is what I'm mounting. And I'm mounting the checkpoint and the Spark state. These 2, you will see the importance once we get to Spark, when we get to creation of the Spark jobs and all that. But for now, let's keep it as it is, and please remind me. Maybe not, you may not be able to, but I'll make sure I remind you of this bit once we get to that point. Okay, and that's it. So let's start up our master worker architecture. So master worker architecture is pulling and downloading, so that should be less than a minute as well. Okay, took 43 seconds to do that. And if you check that on the UI, on my Docker dashboard, I have my Spark master Upstack dashboard, not the Docker dashboard. I have my Spark master, which is on this port, and you can check that out on here. So I just need to, yeah, 9190. So if you look at this, I have my Spark master here, and right now I have 6 scores and 6 gig memories, which means each of my workers is carrying 2 cores and 2 gig of memories that can be used. So I don't have any applications running, and if you check each of these guys for the executors, right now none of them is engaged. So it's good. So we have a Spark master worker architecture all connected. The master is connected to the workers, and it can start distributing those tasks to the workers. Now let's get into the production. Like I said, for the production we are going to use 2 approaches. One is Python and the other one is Java. So from my experience, if you use Python, you may not be able to, unless you have multiple ways of running this. Maybe you run it on multiple terminals, or you parallelize this in some ways, but it's going to reduce the number of throughput that you have. If you are, the more threads you have, the more resources you use, and the throughput goes down. So if you're using 1 or 2 threads and multiple terminals, you can still push your production up till about 50K. But that's the best that I've seen so far when I tried this. But if you use Java and you apply similar logic on multiple threads, multiple instances, you can push up until maybe 250, 200K. I have not been able to replicate 333,000 records per second. But what I was able to push up to was 150K on a single thread, about in 2 instances about 250K as the maximum throughput speed that I've been able to do per second. Yeah, but that's not to worry. So you don't have to worry so much about that. If you have a system that is able to accommodate those data, then you're still good and you're on the right track. Okay, so now let's get into the production. So the first thing I want to do is, in my main, I need to change this. I need to install the packages that will be used. So pip install Confluent Kafka. So you need the Confluent Kafka because that's the one we generally use to do the production. So what I'm gonna do is from Confluent Kafka, import the producer. Yeah, and from Confluent Kafka, I'm going to be importing the admin and the client, admin client and the new topic. And the reason is because if you just create the producer, by default, you're going to have 1 partition and 1 replica. So in our case, we want to have 3 replicas and maybe 5 partitions. It could be less, but let's stick to 5 partitions and 3 replicas. Yeah. So I need to have an entry point. If the name equals to main, of course, then I need to start with the production here. So I need to first create topic. So I need to have a function to create the topic, and the topic that I'll be using is going to be a topic name. So this is where I pass in the properties of the topic and the replica information that I want to use to generate those topic, right? And of course the partition as well. So while this is true, I'm going to, yeah, maybe I should first start with the function. So I just need to create the topic, and I'll call this topic name. Yeah. So I'm going to have my admin client, literally on my Bootstrap servers. I need to get in my admin client for my Bootstrap servers. So it's using the localhost 29092, but I need to have my Kafka brokers here. That would be localhost 19092. If you check this bit, we're using 19092 as our Kafka broker, but for the advertised listener, I have 39092, 29092, and the last one, where is it? For my first broker is 29092, 39092, and 49092. So I need to use that. Localhost 39092 and localhost 49092. Yeah, those are my producers, my Kafka brokers. So I just need to change this guy to Kafka brokers. Yeah, so my admin client is kind of connected to my brokers, and I can use that to create a topic. So to do that, I need to first extract the metadata for the topic that I want to create. So I just need to list the topics, and I just need to put it a timeout. It's going to be 10 seconds. So when you list the topic, if the topic name that we are passing into the topic is inside the metadata.topics, you could check that out, but I don't have that time. So the topic is going to be new topic. So if the topic name is not in there, so we create a new topic and call it the topic name is going to be topic name, and the number of partitions is going to be number of partitions. So let's get that in. Num partitions is going to be, let's call it 5 partitions, and the replicas, replication factor is going to be replication factor, right? So I just need to get this guy here as well, and it's going to be 3 replicas, no, not 2, 3. Yeah, so that's the replication factor that I want to have in there, and that's it. So I just need to now force the admin client, not force, to direct it, and that would be fs is going to be the admin client dot create topics, and we're creating the topic that we just passed in. So for the topic that we're creating, we create a feature here in fs.items. So we try to get the future result, because that's the result once we trigger it, and then we call this print topic name created successfully. But if it fails, just have an exception here, exception as E, and then we say failed to create a topic, failed to create topic name because of this. Yeah, because of this reason. Okay, maybe not, I don't need to wrap this, it's fine. Good. And that's all I need to do for that bit. And for the exception that is generated from here as E, I'm just going to print here. I'll call this error creating topic, and the error is E, right? So what that means is I'm creating the topic here. If it fails, I'll say error creating topic. Now, but if the topic is already in the topic, so I don't need to go into the error mode. I can just else print f topic already exist. Good. So one bad thing that I'm doing right now is using print. So let's get in our logger. So I just need to import login for the logger, import login, and just configure my logger, and I'll say login.basicconfig, and the level is going to be login.info, and the format of the logs, I don't really need to format it anyway. I'll just leave it as it is, to be honest. Just login.info, and I'll change this to login.info. Yeah, and there's an error here, so login.error. Not login, so I need to get my logger here. So here will be logger. It's going to be login.getLogger for my name, right? Yeah, and I can use my logger. So instead of login directly, I can use my logger here. Yeah, logger.info, and here logger.error. Yeah, that's fine. That's all I need to do. And at that point, I think that should be pretty straightforward. And yeah, so I have my create topic, which has a topic name that I'm going to be using. So, but I don't have a topic name yet. So I need to move this just up here. Topic name is going to be, let's call this financial transactions, right? Without data inside it. So let's see if we're able to create this topic. Python main.py, and it says info of main, topic created successfully. So let's see if we are able to do that. If I refresh this page, I have financial transactions with 5 partitions and 3 replicas. Good. So that means we are on the right track, and we can proceed with the rest of the production and the data generation. So for us to generate the data, we need to have a while function here, because we just want to continuously generate. We have transaction is going to be generate transaction. Yeah, and we need to have a function that does that. We just need to create a function up here and call this generate transaction. Yeah, it's a single record, so I'm just going to be returning a dictionary of object, and that is going to be transaction ID is going to be a string of UUID dot version 4, right? The user ID is going to be a comma, right? A round of, no, that's not user ID, so it's going to be f of user and random dot rand int. I'm going to have, just let's say we have 100 users, right? It could be more, to be honest, but just leave it and make things as simple as possible. The amount is going to be uniform round of random dot uniform, and it's going to be between 50,000 and 150,000, and I'm rounding that to 2 decimal places. Yeah, the transaction time is going to be the integer version of the current time, right? Dot time, and that's going to convert it. It's going to do the import, yeah, import time, yeah, automatically. So just make sure that your imports are right, and you should be good. The merchant ID is going to be a random choice between, let's say, merchant 1, merchant 2, and merchant 3. So just in case, this is not the right ID. Of course, if you have a real system, this is going to be like an ID to the merchant, of course. Transaction type is going to be a random.choice, and we're going to have maybe a purchase, and refund. Then we have the location. It's going to be location underscore random dot random integer between 1 and 50. Yeah. And we have payment method, payment method, which is going to be random dot choice between a credit card, just like we mentioned, a PayPal, or even a bank transfer. Yeah, bank transfer. And then it's international transaction. It's going to be random dot choice true or false. Yeah. And the final thing is the currency, right? Random dot choice between USD, Euro, and GBP. Yeah, choose one. Good. So that's the dictionary that we are returning. So once you generate a transaction, the next thing is to produce. But we don't have a producer, right? So, but we have a broker. So we need to configure a producer that will know and that will be used to understand what the producer configuration will look like and how it should interact with the producer on Kafka. So I'm going to have producer conf. It's going to be my bootstrap.servers. It's going to be, of course, Kafka brokers. Then what I want to do is additional fine-tuning. This is not necessary if you are using a development environment, but in a production environment, you might want to include something like this. It doesn't have to be. So we are looking at 100K records per batch, right? And that's for the buffering. So just in case multiple records are coming, we can acquire up to like 100K records per second. But the problem is, no, not per second, but per batch. But the problem is, if you are doing 100K records in each batch, do you have enough memory? That's the question. Do you have enough memory to keep track of 100K records in memory? Maybe not. So in a real sense, you wouldn't use 100K records to keep in memory. You might want to reduce this a little bit for the maximum number of messages that can go into the queue at a time. And if you keep this too low, for example, if you say 100 records per queue, that means if 100 records are being sent to Kafka at the same time, but in the meantime, there are still more records, let's say 200 records coming in at the same time, then 100 records will be in the queue, the rest will be dropped. You don't want that. So you don't want to lose transactions coming into Kafka. So this piece is a little bit tricky. You can add it if you know what you're doing, but you don't necessarily have to. That's the whole point. And then so you don't, and if more records are coming in above your buffer size, which is the maximum number of messages that you want to have in the queue, it's going to tell you queue full. So you're not going to see those records in Kafka. Yeah. Then the queue dot buffering dot max in KB size kilobytes. Yeah, you have 512,000, and that's usually 1 gig buffer, right? That's 512 MB, 512 megabytes, not 1 gig. Then you have your batch number, the number of batches. Well, I'll just leave this here just in case you want to configure your production environment. I'll leave it as 1000 batches, and the linger ms. And the reason for this is because I'm leaving it at 50. It's just like to give some time for production to be done, 50 milliseconds. This might be expensive in a real-time system. Yeah, maybe you don't have to have it, but I'll just leave it here. Maybe I'll leave it as 10 milliseconds. Yeah, and acknowledges is 1. So just to make sure it acknowledges each record. Now this is the bit that you need to do the compression. So the compression type for this data that is going into Kafka is going to be gzip. Yeah, I'll leave it at that for gzip to do the compression. You can also use snappy if you prefer, but I'll leave it as compression type, right? And then my producer is going to be producer for the producer configuration, and that's it. Yeah, that's it really. My producer is ready, and we can use the producer to produce some topic, to produce some data into the topic rather. So I'm going to have to try to produce producer.produce, and I'm producing into what topic? The topic name. Yeah, and I'm producing what? The key is going to be transaction, and I'm extracting the key of user ID from there. Then I'm having my value as json.dumps. Don't use the dumps. So that will be the transaction, and you can encode it in UTF-8. So if you prefer, you can add the encoding. I'll just leave it at that. I think encode in UTF-8 format or something like that. Yeah, if you prefer to use the encoding, if your data has some custom data that are not in the standard format of UTF-8, you might want to encode it into that. Then on delivery, what happens? We want to get a delivery report. So to do the delivery report, you need to make sure that, so the delivery report is once you send data to Kafka, you get an acknowledgement message that the data has been produced. That's as simple as it gets. I'm going to have a function called delivery report, and I'm going to have the error and the message. So if there is an error, it comes first, message comes next. So if there is error is not known, I'll just print the delivery failed for this record of message. Maybe not mess, I'll change this to message. Yeah, so that will be message.key, and I can escape that. Otherwise I'll just say record with message.key successfully produced. Yeah, okay, so that's my delivery report, and that's going to be sending the data into Kafka. And in the meantime, I can say for each of the records that is being produced, I want to log that as a produced transaction of this transaction information, and then producer.flush. Yeah, and somebody will ask, one sec, accept the exception as E, and I'm going to print error sending transaction of E, right? That's the error. Okay, so the reason, so somebody may ask, why am I doing flushing here when I have my delivery report? So what happens is, for each of the records that are produced to Kafka, I want to get an acknowledgement message before producing the next one. So that's going to add a little bit of overhead, but it's important for each record that I'm producing to get delivered to Kafka, so the queue gets refreshed on time, right? So you can do away with this and you still get your production as it is. But just in case you want to read more about the flushing and polling, it's just you need to go into the documentation for that. I may not be able to go into the details of all of that. But what happens is, on delivery, you get an acknowledgement message, whether it's successful or failure. But usually if you don't have something like printing here, that would be after you stop the production that you see your delivery messages. Okay, and that's it really. Anything else? I'll leave it as it is right now. We can improve this and put it on multiple threads and see if our production is going to increase or not. If it is not, then we just leave it as it is. Okay, but for now, let's see if we can produce some records into Kafka. It says compression type. Let's see, something is missing from here. Compression, no, it's compression dot type. Yeah, it says two choices. So I have, let's see, it should be an array, right? Yeah, so it's producing the data, and you can see the data being produced. So let's check what the data looks like on Kafka. So if I refresh this is 5,000 records. So it takes I'll just refresh 9,000. You can see it's about roughly 1K records per second. Yeah, this may not be visible to you for now, but if you take your time to look at every second that I'm refreshing, it's literally about 1K records that is getting produced per interval. So yeah, so this is not gonna work. To be honest, it's not gonna work. The production is too small for us to have 1.2 billion records per hour. But what we want is to have about 100K minimum, maybe 200K being produced into Kafka. Okay, so let's see if we parallelize this, we can achieve some higher level of production. I'm going to just try and have a function here. Let me see. Create topic, blah 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 blah. Yeah, so I'm just going to have a function here called this produce data in parallel, right? In parallel, I'm going to have a number of threads, num threads, right? I'm still unconvinced that this is going to improve the production, but for now, let's just give it the benefit of the doubt, right? So I'm going to have threads, and I'm going to have an array of threads here, and I'm going to have to move this bit a little bit away from here and put it in the dev produce transaction. Yeah, and I'm going to put this here. Yeah, okay. So we obviously know we are maybe 1015 records max per second, but we want to put this inside a thread, right? So we just need to have a try catch here for the data production inside the thread. So I'll say for I in range of num threads, which is the num threads, which is the number of threads that I want to produce data to. I need to have a thread here, which is going to be threading. I need to pull in threading dot thread. Okay, and I'm going to have a target. The target is the one that I want to use to send the transactions, right? So that will be produce transaction, and the argument, if there's any, in our case, is going to be the thread ID that I'm using to produce, right? Args is going to be I comma, right? So, and exception as E, print error message. Yeah, as E. Yeah. Okay, so what I'm doing is I'm producing the transaction, and I need to have an argument here. So I'll just say thread ID. Yeah, I'll come back to this later, but let's finish this threading. So I'm going to have threading thread.daemon is going to be true, thread.start, and threads.append the thread. So if you have two threads, it's just going to keep them in this array, and then Once that is done, I just do for thread in threads. I say thread.join because I'm starting all of them. So, and that should be fine, really. This is going to join them back to the main thread, and that should be okay. And the final thing is when I'm sending the transaction, I have a thread ID. I want to just to show which thread produced what data. Here, when I'm producing the transaction with the thread ID, I'll just have thread ID. Yeah, produced this particular transaction. Okay. All right then. I think that's all we need to do. Yeah, that's all. I just wanted to try that. So let's see if we are able to produce in parallel for this. So we have produce data in parallel that we need to call. I'll just call produce data in parallel, and I'm going to have my number of threads to be 3 threads for now. So let's run this main py, and you can see I have thread 012 producing the data, and let's check if what that look like. It's still like 1k 1 2 3 4 5, right? So it's about 1k records on the average, which is still not what we want, to be honest. It's still not what we want. So what can we do? So what I can do is to see the major difference. This is on a separate thread, but what that means is if I try to have another thread here, another terminal, and I try to do the same python.main, now I have two threads in parallel, and I have 100k records. Let's see if we are producing more than 1k now. Yeah, we are definitely producing more than 1k. We're about maybe 2 or 3k into the picture, but how many threads can I successfully create? How many terminals can I successfully host this? Python main py, and let's have just one more. Python main py. Okay, so I have 5 terminals with 3 threads each, so that's like 15 workers producing data in real time. And let's see what that look like. Literally about 3k records per second. That's the throughput. Yeah, it's still not satisfactory, to be honest. About 3 to 5k, still not satisfactory. So what I'm gonna do is put a stop to all of this. But at least you get the point, right? So it doesn't necessarily matter if you're using Python or Java. And by the way, I'm open to a different way where we can push this production to 100k per second. But that I haven't been able to push it for a single record per second, 300,000. I have not been able to push it. And I'm open to suggestions. If anybody is able to do that, please let me know in the comments, and you can share your code with me as well, so we learn from each other. Okay, so that's a good one. But alternatively, I have written a similar code on IntelliJ IDEA, and I'm going to share the code with you. So what I'm doing here in IntelliJ IDEA is this. I have a transaction producer, which is this. I'm calling this, and I'm just pushing these financial transactions. I'm having my bootstrap servers, the 3 bootstrap servers, my number of partitions, my number of replicas here. Maybe I should just increase this a little bit. Yeah, that should be fine. I have, I can expand this. So I have the number of threads. I'm using 3 threads here, and I'll see if I increase the number of threads. Let's see what the size will look like. So the number of partitions is 5, which is the topic that we have. The replication factor is 3, of course, and I have a create topic, similar code, the same configurations. The only thing that is different is the batch size config, which is 64 KB. But it doesn't necessarily matter, because it doesn't matter what you use as your batch size config. If your system is not able to push to that, there is nothing you can do. The compression type that I'm using here is snappy. The acknowledgement configuration is 1, which is literally the same thing in my configurations here. Yeah. What I'm doing is to have 3 executors, 3 threads. So I'm doing a loop. For each of the executors, I'm submitting the data into the Kafka producer. The Kafka producer, which is of course the library for producing the Kafka, which is already in my pom.xml. And I just do a loop. My transaction is this, so it's not different to what I had before. If you look at this, it's literally the same thing. Yeah, literally the same thing. And what I'm doing in the random transaction is just like I'm doing in the dictionary in Python. Yeah, I just generate the transaction, I write the value as string, I converted everything to string, something like this, and I write them to Kafka, which is the production that I'm doing here. So if it fails, then it sends me an error message. If not, it says it was sent to partition, and that's it. And I just try and monitor the throughput for every 1,000 records in terms of checkpoints. I want to see the number of throughputs that I have in there, and that's it really. So for creation of the topic, if it doesn't exist, what I'm doing is just like as it is, that I'm connecting to the Bootstrap server, and I'm creating the topic if it doesn't exist with the number of partitions and the replication factor, and that's it really. So what I'm gonna do is take this for a spin, and we can see the difference. Right now we have 273,000 records. So let's see how many records you can produce in 10 seconds. So I'm going to start counting, right? Run this. And I'm going to put my terminal. I'm trying to see if I can. Yeah, I already started it. Let me see. Yeah, here's my terminal. So it's producing this data, and you can see that it's producing them to the offset. So let's check what size we're able to produce. Now we're in 66 million. So let's check. Every second, I'm going to count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are literally producing over 100k records per second. So I'm going to just enable 10 second refresh. So this is 9.7 million. And in the next 10 seconds, once it refreshes it, we see the number of records that is in the topic. We have 12 million records now, 12.5 million records. So the next 10 seconds is coming up shortly. Let's see that. 14 million records. So every 10 seconds is about 2.3 million. That's like 230,000 records, is it? Yeah, let's see. 2.3 million. Yeah, 2.3 million divided by 10 seconds. About 230,000 records. And that's because I'm running on one single thread. If I'm running on multiple threads, I can potentially run up to maybe 250, 300k, to be honest. And that's the difference between something like Java in terms of production and Python. It's just not comparable. Maybe I'm not writing the code right, but the same simple code that I wrote in Java as compared to the same simple code that I wrote in Python, it's just uncomparable. The results are totally different. Now we're about 25 million into the production, and this is like heavy production. So I believe before we finish coding the Spark master, we'll have reached almost 100 million. Let's see, and let's see what that look like. Okay. Now, the second bit of the problem we want to solve is for the production, the consumption of the data. So let's potentially say we've potentially solved the problem of production, which is about 300K, give or take, right? For the consumption of this data, we need to have our Java, which is, sorry, not Java, our Spark code that is doing that. I don't know, IntelliJ that just entered my head. So, yeah. So what I'm going to do, I'm going to take a pause because it's going to slow down the system. So I'll just take a pause on this production for now. Yeah. And yeah, that's it. Really, I just take a pause on that and push this back to okay. So now we need to create a consumer as usual. It's like a day job here. So we have our jobs. So inside our jobs, we have our Spark processor, right? .py. I'll try as much as possible to make this like production compatible, but it doesn't necessarily mean like a copy paste into production. So you need to like still adjust this code to suit your production use case. So pip install PySpark. Okay, and I'm going to have from PySpark.sql, I'm going to be importing Spark session, and from PySpark.sql the functions, I'm going to be importing every functions that exist in there. So if the name equals to main, this is not necessary for a Spark job, to be honest. So I just want to do that for like in fact I don't need to decorate this. So I just have my Kafka broker, just like I had in my main. Just copy this. Yeah, paste that in there. My source topic, which is where the data is coming from, is going to be financial transactions. Is there hairs to that? Let's check. Financial transactions. So we have 42 million records in 11 gig, which is not bad. I mean, we can work with that. It's a demonstration. So then we have aggregate topics. So we want to do some aggregation. Now we call this transaction aggregate. And let's find an anomaly. Anomalies are as simple as a high volume or I count, right? Anomalies topic. I'll call this anomalies transaction anomalies. Good. And final thing, we have our mountain that we did earlier for our checkpoints and Spark state. We need to recognize these guys. So our checkpoint is going to be this checkpoint directory is going to be this, and the mountain is going to be state directory. It's going to be that. Good. Then we just need to initialize our Spark. It's going to be Spark session .builder, and so if you don't want to have the backslash at the end of the code, you can just put a bracket before and after. Then you can easily just do that. And I can have the name financial transactions processor. The configs that I want to use, I'm going to maybe copy paste this. I have Spark. Maybe not. Let me just give it a go. Packages, and that would be org.apache.spark, and I'm gonna get it from Spark SQL. Yeah, Spark SQL Kafka. Just in case you don't know how to get this, you just go to Maven repository.com and you search for Kafka Spark SQL Kafka. If you search for this, you see the 010, and I'm using Spark version. If you check my Spark version that I'm using, that's 3.50. So you need to check 3.50 as your code. And in the Maven repository, you need to copy this bit. So I'm just gonna copy this artifact ID, no, the org ID, which is this guy. I'll copy that, and in my Spark processor, I'll replace this, and then full column. Then I copy the second bit, which is this guy, artifact ID. I paste that in there, and full column again, and the last bit. Now the challenge now is we don't know the Scala version that I'm running on my Spark. So to check that, you need to first go into the terminal for your Spark master or worker, because they are using the same thing. So you can check Spark shell. If you do Spark shell, you'll see the Scala version, or you just type in Scala -- version. That works as well. But if you type in Spark shell, it's going to go in there and show you the, no, I'm just gonna Scala version, right? Spark shell. That's interesting. Yeah. Oh, Spark shell version. So you have, I'm using Scala version 2.12 and Spark version 3.5. I thought I could type in Scala -- version actually, but it's fine. So you could just use Spark shell version, and it's going to spit out the version of Spark that is currently in use, and this version of Scala that is currently in use by your container. So I'm using 2.12, so I need to change this code a little bit to reflect 2.12. And if you check my this guy here, and you go one step back, you see that here for 3.50 you have 2.13 and 2.12. So you should use 2.12, not 2.13, okay, in my case. All right, so that's my configuration for that, and I have additional configuration that I want to put into picture. SQL streaming .checkpoint location, and that will be my checkpoint directory, and then config again Spark. If I'll just duplicate this, SQL streaming states store directory, state store directory, and that will be state store directory. Good. And the final thing is the number of shuffle partitions. I'm going to tell you why this is important. So we have shuffle.partitions. So in a production environment where you have, let's say, 5 partitions, right? That's not heavy partitioning, to be honest. In some real cases, you have like maybe 100, 200 partitions. So what happens is when data comes in, it shuffles in, and the first partition it says is what it uses to process the data. Instead of waiting to get to the partition number before it processes it, it just shuffles the partition and then processes that data as it comes in. So in a real sense, you want to increase the shuffle partition to be a little bit bigger, but not too big, if you get what I mean. But I think, yeah, you get the point. So if you want to get more information about that, the shuffle partition, the details about it, you can go into the documentation for that. So I have my Spark context, Spark context, and I set the log level to 1 in. And this is not necessary. This is just like a decoration on a cake. So the final thing is to get in my schema, not the final, well, semi-final. We're still getting to the last bit. The transaction schema. It's going to be a struct type, of course. So a struct type of a struct field, and you need to import struct field. Yeah. So I'm going to have transaction ID. I think that's it. So yeah, you get the string types, the double types, and yeah, and that's it really. So once you get the transaction schema into the picture, the next bit you want to do, yeah. So the next bit you want to do is make sure that you're able to read data from the Kafka stream. So you have Kafka stream. It's gonna be spark.readStream, and I'm reading the stream of data from the format. I'll just put this bracket around it, and the format is going to be Kafka. And the good thing is you already imported SQL Kafka code, so you're good to go. The option you want to use to read it is going to be kafka.bootstrap.servers, which is the Kafka brokers. We have additional options. We are subscribing to what topic? Subscribe to source topic. And final option here is going to be the starting offset. Where do we want to start? Starting offset. So where do we want to start from? So I'm going to be starting from earliest. Now it gets tricky here. The first time you run this, it's going to be earliest. So once you finish processing the backlog, you need to change this to latest. Otherwise, you have to keep running everything from the start again and again. So you don't want to do that. Okay, I just do .load and we're good to go. Cool. Now we can we have the Kafka stream. So the next thing is to extract data from Kafka stream, and that will be our transactions data frame, which is going to be Kafka stream dot select expression. Kafka stream dot select expression. We're going to extract the value from there, so that will be cast value. So usually you have key value headers, right, and additional stuff like that. So I just cast the value as string. Maybe I just put this in caps, and yeah, and I'll just select from there. So once you cast the value as a string, you cast it. You convert that value that you just casted as a string. I need to close this bit. You need to convert that value into a JSON. So I'm going to have from JSON. So in a case where you have Avro as your encoder for the schema, you need to from Avro instead of from JSON. Then if you have something like Paquet, you need to change this to something like from maybe Paquet or something like that. Yeah. I hope that's right. I'm not sure. I have to check that. So I have my from JSON for the column, and I need to pass in inside the from JSON. I need to pass in the schema, so transaction schema. Yeah, and once that is done, the only bit that is left is I have that the alias. Yeah, I alias this as data. I'm selecting yeah, select from JSON the column value transaction schema the alias, yeah, and I just select from here, just select data.aesthetics. So I'll explain. So what I'm doing is casting the value. I told you I have key value headers. So I'm extracting value from there when I do my select expression as a string, and I'm converting that to JSON by doing from JSON. So it converts that value to string in here, and I pass it to the transaction schema. So it deserialize that into this schema object. Then I alias that as data and select that from there. Now, once that is done, the next thing is to if you want to have a derived column. So in our case, we have a transaction time, right? So transactions df is going to be transactions df dot with column. So we're doing what's our column transaction type here? Transaction time. Yeah, just converted that to. So we need to change the name, right? Transaction timestamp. And we just need to extract that from column of transaction time, and we can divide that by, because it's in milliseconds, we can divide it by 1000 to convert it to seconds, and we just cast it as timestamp. Yeah, sounds good. So we extracted the time divided by 100 and 1000, then we convert it to timestamp. So the simplest aggregation logic we want to apply is just to aggregate the merchant and the total per each merchant. You can increase the logic or make the logic as complex as possible, but for now we just keep it simple. So we just have aggregated df aggregate the data frame. It's going to be transactions data frame dot group by, and I'm grouping by the merchant ID, and the aggregate is going to be the aggregate. I'm aggregating the sum of amount and aliasing that alias as total amount, while the count is going to be count of star alias of transaction count. Yeah, good. So with that said, I can now write this aggregate into Kafka. So I can have aggregation data frame. It's got aggregation query. It's going to be aggregate df dot with column. I'm going to have the key. So I'm reformatting this back to Kafka format. So I'm going to have the column of merchant ID, and I'm casting this as a string. And the value is going to be value, and the column is going to be to JSON, and I call the struct of the column of merchant ID column total amount, and the final thing is transaction count column transaction count. Yeah, and I just need to close up my struct. Yeah, and that's it really. So I have just on the same line. So what happens is I have my struct as my merchant. Yeah, I just have all of these groups, and I'm trying to refactor them to Kafka format so I can write them to Kafka. So I can have my select expression as my key and value, which I need to write to Kafka. I just put this inside the bracket. My select expression is going to be write stream, and the output mode is going to be Kafka, and the option, the format, so the format is rather Kafka. The output mode is going to be update. I just want to keep updating the data as it comes in, and I have my option for kafka.bootstrap.servers, which are the Kafka brokers, yeah. And my option for the topic is going to be aggregate topics, right? Then the checkpoint is going to be the option. It's going to be checkpoint location. It's going to be the checkpoint directory / aggregate, right? Aggregates. And that's it really for that particular writing to Kafka. And I can just start this. So to JSON, I'll close this. Yeah, I'm writing everything to, I can start this. Oh, I can just aggregation query dot start. Yeah. That's gonna be a problem. So I just put a backslash at the end of all of this. Okay. Yeah. So I just put the backslash at the end, and that should be it. So if I run this, I'm expecting to see those aggregations on Kafka. So let's see if that works just fine. So docker exec again and submit. So I just started it. I didn't await the termination, so I wait termination. Okay, so let's see if data is written to aggregate topic. So I just go back one step and I should refresh this. So it's not getting written into this. So it says missing one required argument in line 55. So it says we have with column value So I have my with column value, but I have a closing bracket here, so that's wrong. Yeah. A select expression is here. No, I need to close this with column here, and I can start the await termination here, and that should be it. So that should be fine. Okay, let's check this out. There's an error, right? Is there? No. Okay, I'll just refresh this. And it should be able to clear up the states and checkpoints in memory already, and to be able to continue from the start. I believe this should fix it. If I refresh this UI, yeah, that should fix it. Let's see. I'm just going to produce a couple more records. Yeah. And refresh this page. Yep. So the transaction aggregates are getting pulled over now, and if you click on the transaction aggregates, you see a couple of records here. So let's produce more records and see if we're able to see them. Okay, so that's producing, and that's going on in the background, so we just wait for it. So how many records do we have here? 7,000 records, right? And if you check again, we have 4 records now. Okay, so partition 0, merchant 2 is dropping. Let's see, 7 records, right? And we have new records in. So for the latest merchants, 1, 2, 3. So let's check merchant 3. Here we have 9,500 records for this merchant, and previously we have 8,000 records. So about 1,000 records per second is actually getting pulled over from here. So yeah, data is growing, and we can easily connect this to some visualization UI and all that. But what I want us to go into is if you go into localhost 4040, which is the job, the worker information that shows you the job that is currently running. If you go into the localhost, you see the jobs that is currently running. Here's the event timeline. You see the number of executor that was added. That was maybe when these are the 3 executors, 0, 1, and 2 that was added. Once the executor driver was added, this got added, and subsequently we have some job submission here, which are the batches that are coming here. Yeah, that's going on. It just keeps going on and on. So while that is going on in the background, let's take a look at some of the completed jobs. These are them, but we're not going to focus on this. Let's look at the structured streaming, because that's what we're doing, right? So if you click on the run ID, you see the number of records per second that is getting processed, and right now we're about 379 records in per second. What that means is the number of records that is getting produced successfully into Kafka is about 300 records. Let's add additional production to this, maybe 2 or 3 more productions, and see what that look like. So we have 3 more. So technically that should raise up to about 1K, right? About 900 1K per second. So it takes about maybe 2 or 3 seconds, less than more than seconds. I mean, maybe a minute or two for that to actually reflect on the timeline dashboard. But we just wait a few seconds for that while the production is going on, and we should see what the input rate looks like, the number of records per second and the processing rate. And obviously the operation duration started just like very high, and then it balances down at 5 let's see, yeah, this is about 5,000 seconds, milliseconds, right? So literally about maybe 5k milliseconds. So that's like 5 seconds for each batch. But what that means is we're not processing enough, because if we have more records in the batch is definitely going to slow down, unless we had more executors into the mix. But we're always going to have a slower batch. Now we're going to see the difference. If you look at this, we were able to push up to 1k at some point, then it dropped to 500, then to 800, now to 500, and the batch duration drops drastically as well. So this doesn't necessarily mean a good thing, and it's not necessarily a bad thing. I mean, it's just that we are not having enough data getting into Kafka for processing on time. So what I'm gonna do is cancel all of this. Yeah, I'll cancel this, and we just have our consumer in progress, and just one of these. I'll just stop this as well. So let's see what that look like. Right now, we're still picking maximum record at 453 records. This is not enough. So this is what I was talking about when I was talking about Java to Python the other time. So with the transaction producer from Kafka, so let's see what that look like when I initiate this from Kafka. It takes less than 30 seconds for it to reflect on the UI. So we'll just wait a couple of seconds for this to reflect and see what the changes look like. Okay, so right now the last batch was 271 record. When we started the production with Java, let's see what that looked like. If I refresh this again, it's still not reflecting yet. We wait a few more seconds. Not yet. Yeah, you can see the batch duration is getting increased now. So before now, we had a peak of 62,000 milliseconds for the batch duration. So let's see what that look like now that we've changed our producer to Java. So it's picking up anyways, but we're still not there yet. It hasn't reflected on the input rate and process rate. Still waiting for that to come in. Still have one structured streaming that is happening. Okay. Yeah, and you can see the difference. Now we were before now we are at about maybe 1k, right? As the maximum. Right now we're about 73,000 records per second, and the processing rate has increased drastically. So you see the difference right now, and this is just like on a single app that is running on 3 threads, right? If we increase this to like two applications that is running on, and I'm sure this is going to increase. If we run the 2 applications, that will be 6 threads running in parallel. I'm sure we're going to have way more records per second once the system picks this up. And this is not just reproduction. This is for like Spark receiving those records and trying to process them. Yeah, this is going up drastically, and the aggregation number of state rows is also increasing drastically as well. If we wait a couple more seconds, you see the latest information. So this dropped again to 24,000 records per second. Yeah, this has stopped. That's why it stopped. I don't know why it stopped. It shouldn't stop, right? I'm doing a while loop. Yeah, while true, right? It shouldn't stop. Maybe because my system RAM is getting used up. That's why it's stopping. Yeah, but you can obviously you can see the difference between when Python is producing and when Java is producing. It's just like incomparable, to be honest. But maybe I'm doing something wrong, or probably my local system is just like not as supportive of Python as compared to Java. But the difference is night and day. Yeah, this has stopped for a while. Is it still producing? Yeah, it should pick up again. I'm interested in seeing what the numbers will be this time around. Are all my brokers still active? Yeah, one is down. Well, the good thing is it's always restarting, so just one of them is down 8 seconds ago. Yeah, that should be fine. We should see a change in the graphs here. I'm just going to try and restart this guy and see if we can reproduce the same thing on the UI. So obviously it has stopped at some point. I'm just going to restart that. I don't know if yeah, we're still working, and you can see we are back to about 60k records per second, 73k, and input rows 2.9 million, and 548,000 milliseconds. So it's taking more time to process the data, and of course that's expected because the size is getting bigger. And this is where Apache Spark is a little bit backward, because if you're micro batching and a lot of records are in the same batch, obviously it's going to slow down the processing as compared to something like Flink. Flink is going to process individual records and not micro batch them. So while this is a good thing for Apache Spark in some sense, it's still like a downside in some other sense as well. So let's see if we're able to push this above 70k. We're about 73k in, so still like processing that. I don't know how long it's gonna take, but to reflect on the UI, I mean, just going to refresh this. And let's see our transactions. So many transactions do we have now? Yeah, the cluster health has degraded. Just one guy is running the entire show, so that's why everything is just like down. So I'll just leave it at that. Let's check the topics. 11 gig. We're 11 gig in, and we are unable to see all of them. We have 42 million records, and let's see what we have in the transaction aggregates. Are we able to restore the, yeah, there's still one more that we're waiting for to join the cluster. Apparently everything is just like keep going down because everything is running on my local system, so there is no way to really ensure high availability on my local system. My controllers are fine, It's just that the brokers are finding it difficult to keep up with the traffic. So the good thing is we know that for sure we're able to produce up until about maybe 250k, and 250k per second is about 250,000 times 60, 3,600, right? We're about 900 million records per hour. So we're able to push 900 million records per hour, but the processing of that is another challenge, because on my local system I have 3 workers, and the three brokers are struggling to keep all the data intact and not shut down. So yeah, as much as possible, while I was able to process a couple of records, millions of records, but it's still not enough, and that's why you need a dedicated system to process all of this data. And to be honest with you, if you want to run this in production, it's not going to be on Docker. It's going to be either on Kubernetes or a bare metal. So that way you can control the data better, the architecture of the system better than what you have on Docker. Right now, it works just fine for me when I'm in dev mode, but when I'm in production mode, it's a totally different ball game. So you could have more workers, more brokers, and as much as possible, you want to have much more size, which is my constraint on my local system. So 900 million out of 1.2 billion is about 75% there. So yeah, we are 80% there. So we were close, but it's just not enough as much as possible. So if you get 80% in your pass mark, I guess that's a good mark, isn't it? So yeah, let's wrap it there. I'm going to try and push this. If I'm able to push it to maybe 1 billion, then we can see if I'm able to do that. But if not, I'll just keep it at 900 million records. If this is your first time joining the channel, or the first time of watching our videos, please make sure to like and subscribe, and don't forget to share with your friends and colleagues. So thank you very much for joining the video and for learning with me. I'll see you in the next one. Cheers.